positions started to contaminate the protocol. Just to give you an idea of the kind of signal and noise that's required to get that sort of measurement, this is beta that shows the dispersive line shape associated with the cavity resonance readout. And for our parameters, the cavity had a line width of on the order of 8 kilohertz, and the index refraction frequency shift for a single atom was about 5 hertz. And so by having enough photons in this signal, you can, when you make a measurement, infer on photodiode with a homodyne signal, a homodyne readout, the cavity resonance shift from the position on this dispersive curve, and hence make the inference on the number of atoms in the cavity. So a key aspect for metrological utility is to demonstrate that you can have coherence after you've made one of these non-destructive measurements. And it's not at all obvious that you should have coherence. It's after you've done this process. Why? Well, because you have that atom cavity interaction that gives you the dispersive shift that measures things. That's great, but the fact that you have that shift means there's an interaction between the light and the atom. We call it the AC Stark shift, and any inhomogeneity in that AC Stark shift dephase that coherence. So you could, in fact, be making that measurement, and things could seem to be great, but you could be splaying the coherence away with a contaminating shift. And in fact, that does happen if you have the wrong set of interaction parameters. So you have to know what you're doing when you make that measurement. But the amazing thing is that you can get to a point where you can both reduce the number of fluctuations and you can have full coherence. And so that's what's shown here. This is a Rabi flop scan that results from a final coherent pi/2 pulse, which is applied after the state squeezing protocol, showing that you can oscillate the population all the way down to the ground state and then all the way back up to the excited state, as you would expect to be able to do if you had not done a state squeezing protocol. So that is an important aspect of such a protocol. Okay, so I will note that for when you take a closer look at what's going on for these parameters, you do see slight losses in coherence due to the state squeezing protocol, but the overall metrological utility of this state, which is associated with the slope of that line, has barely changed due to this state squeezing. Okay, so this will become an important detail just a little bit further down in the talk when we start asking about how things can go wrong when you want to bring this protocol into the real world. But it turns out that in order for these systems, it's beneficial to be able to prepare the state in such a way that each atom is coupled to the cavity, that is, experiences essentially the same index of refraction contribution to the collective readout, coupled to the cavity in a highly uniform way. And so in our experiment, to enforce that uniformity, we confined atoms to a farty tuned optical lattice at 1560 nanometers, which is nearly perfectly registered with the 780 nanometer lattice, which was doing the Q and D readout. So pictorially, this black here is the 1560 bright lattice, which is very farty tuned, so there's almost no spontaneous emission from that. But importantly, it makes the atoms sit at these positions, which are for appropriate parameters, maximally coupled to the mode function of the standing wave in the optical cavity, which is kind of reading out the number of atoms in the cavity. Right. Well, so I would like to do that. I mean, there's levels of complexity, and so yes, managing the Stark shift from the 1560 lattice was important, and that certainly did set a limit on how well this could work. And sort of what I'm going to explain explain in a few minutes is you'll see the limitations of having 15 systems. Yeah. Right. So subject to those, but this is a good way of enforcing this is a way of enforcing the uniform coupling that we desire. Maybe a better way, which still has not really been realized in the community, is to use a ring cavity geometry where you do not have to contend with the standing wave structure of the 780 nanometer probe. This is what the apparatus looks like. So sort of the point of showing this slide is that in terms of the apparatus complexity, it's not that much of a stretch to get to this point from where you need to be for other precision measurement. I mean, basically, we add two mirrors to an otherwise standard laser cooling apparatus. And once you figure out how to add those mirrors, stabilize the cavity, and do all the rest, it's the incremental experimental complexity is not extraordinary. So it's reasonable to think of this going beyond some heroic experiment that you do in a quantum optics lab to something that's useful for measurement. This illustrates the homodyne readout that we use to detect the cavity frequency shifts. Is more or less a standard setup. And for experts, these are our cavity parameters. The collective cooperativity is close to 1 for this system. So it's not strongly coupled and it's not weakly coupled. It's just right about correctly. This plot here just shows that yes, indeed, that apparatus can read through the claimed dispersive shifts in number of atoms in the cavity. And so when you use this, the apparatus and the methods I just described, you get the data that I showed you on the first slide. So, or the second slide. So it works. You can do precision metrology. I'll show you that in just a moment. But let's take a step back and ask about the quantum mechanics of the states that we're making when we employ such protocols. And so here is a plot that shows, this is following analysis work from this PRL that basically relates the experimental observables, collective observables, the observed state squeezing and the observed coherence to an inferred entanglement depth for the ensemble. This is entanglement depth. It's a measure of how much entanglement persists through the ensemble after you have done this squeezing protocol. Now, why is it entangled at all? Well, you have to have built correlations into the ensemble after that collective measurement. Why do I know you have to have built correlations between atoms? Because if the atoms are all uncorrelated, then the statistics of coin toss wave function collapse gives you square root of n noise. And here I say, well, when I got 1 million atoms and I start flipping the coins and collapsing the state across that ensemble 1 million, that after all is said and done across that entire ensemble, I get noise that's less than the square root of the number of particles. So that means that somehow the atoms across the ensemble know, in the quantum mechanical sense, that if so many have been detected in the upstate, that there got to be so many detected in the downstate. The extreme limit of this is when you prepare so-called dual clock state, where exactly half the atoms are spin up and half the atoms are spin down. And the amazing thing is, as you're collapsing the wave function, it's, if you look at any given atom, it appears to be randomly spin up or spin down. But over the entire ensemble, the statistics work out at the end of the measurement, so half are up and half are down. So there are correlations. Those correlations can be described in terms of entanglement depth. And the bottom line is the states that I've described with that squeezing have an entanglement depth that's around 1,000 atoms. So you could say it's a massively entangled ensemble. Yeah, thanks, Eric. So there's different ways of making the inference entanglement depth from these collective observables, and there's a little bit of theory chatter about what's the appropriate model to use. And so the blue is the most conservative estimate of entanglement depth, and that is a lower this is a theoretical inference. This is not a direct measurement. Thanks for the question. Other ways of characterizing the correlations that exist in this ensemble. What about Bell test? Well, it's hard to do Bell test with this because we don't have access to the position and state of each and every atom in the ensemble. We just have collective observable. So we can only infer the presence of Bell correlations through the collective observables. And I should say that those inferences are documented in this science article. And you can construct a witness, which is a proxy for the Bell correlations that must exist in the sample due to the entanglement. And when you look at this witness criteria and you kind of translate the witness into an effective Bell test, you find out that, yes, indeed, the only way you make these observations is if Bell correlations persist, are persistent through the ensemble. And you're kind of looking forward. It'd be really nice to be able to make, kind of a more refined and, I don't want to say loophole-free, but a more refined and I'd say legitimate Bell test with these types of systems in the future, going to detection schemes where you spatially resolve atoms. Okay, so that's just to say that amazing things are happening with quantum mechanics. It's quantum revolution 2.0 kind of stuff. But at the end of the day, we're talking precision measurement. Is it useful? Can we actually make better sensors? And so here's proof of concept work that Vladimir Voletich is well known for doing the pioneering experiment here back in 2010, where he demonstrated, I think, a 3 or 4 dB improvement in a proof of concept clock. And here's our version of that, where now on the left I show you what the block sphere manipulations are associated with using such a squeeze state in a traditional Ramsey sequence. And so, like, this is the block sphere representation of the first squeezing interaction. That's the probe, which basically reduces the number of fluctuations along the z-axis. The expense of that is that you have to have more fluctuations along the x and y-axis of the block sphere. And then pi/2 rotates this into this plane. The precession associated with the mismatch between the local oscillator and the atomic oscillator leads to the precession of this this distribution, and then the final pi/2 rotates that back on the block sphere. And when you read out Jz, you have basically an inference between phase shift and atom number. And so you can build a clock this way. And clock person characterizes clock performance with Allen deviation. This is averaging time, and this is fractional frequency stability. This is what you'd have if you had quantum projection noise, and this is what happens if you feed it with that clock with the state that I described. You get a legitimate improvement in noise performance of that clock. Looking forward, you say, well, can I build real clocks? Like, this is not a real clock. This Allen deviation is not technologically interesting by any stretch of the imagination. So can I get to a situation where I get interesting Allen deviations of using these methods? And I think we're just at the cusp of seeing that happen now. I want to tell you, what do you need to do to go from here to a more useful clock? Well, for one thing, it's just a bad plan to have the atoms sitting in the lattice, confined there, getting broken up by AC Stark shift from our not magic detuned lattice, and expecting exceptional clock performance. You have to have a way of getting the atoms out of the lattice, making the measurement, and then somehow doing the Q and D detection. So what I would say is, to go beyond proof of concept, we need to figure out how to extend these methods to long interrogation times and also have the atoms be in free space. What's the plan there? So we've been playing around with 2 strategies. Strategy 1 is one where we do the following protocol. We squeeze the atoms in the lattice, then we come bang, bang, pi/2, drive a Ramsey sequence, and then we go back and we do a collective detection again by doing just a silly thing, the experimentally expedient thing of turning the lattice back on and making the detection. And method 2 is prepare atoms in the lattice, release them, pi/2, let the atoms expand, and then detect them in fluorescence. Both have their pros and cons, and let me tell you a little bit more detail about where we are with each one of those. So strategy one, this is what we call release and recapture. And so here's a schematic of the apparatus again. You have the confining 1560 and the 780 nanometer probe. This is a kind of complicated timing diagram showing you what's going on with the microwaves, the Q&D probe, and the confining lattice. And the bottom line here is we've devised a timing sequence where in this window of time here, after this is the Q&D probe right here that basically makes the squeeze state, we have a period in time where all the light is off and the atoms are evolving in free space, and we're doing the pi/2 interrogation. And then we turn this confining lattice back on, and what happens is, if you look at the position momentum distribution of the atoms as they have been released from the lattice, a time evolved in free space, and then when the confining potential of the lattice turns back on, you see that, well, each atom is not staying in the same position in the its momentum is changing, its position is changing, and the bottom line is, at the end of the day, this leads to a change in the coupling function for where the atom was for the first collective measurement to where the atom is for the second collective measurement. And I'll show you in some math on the next slide that this is not a great situation for observing high fidelity squeezing. The bottom line is you need to carefully time up the sequence. I don't have enough time in this talk to go into the details, so that you have some reasonable control over the position distribution of the atoms when you make your Q&D probe. So we actually turn the lattice on for a certain amount of time before we come in with the second probe in order for the momentum position distribution to get to a point where the atoms are well localized again in the lattice. And we're managing not the longitudinal motion of the atoms in the lattice, but the transverse kind of sloshing of the atoms in the lattice. When you release them from the lattice, they expand out, you turn the lattice back on, and the potential wants to push them back together and refocus them, and that's when they refocus, that's when we make the measurement. So what about detection inhomogeneity? Well, you can do, it seems like this may be a completely nasty problem, but it turns out that following the lead from Vladan Vuletic and other theory colleagues, you can do, in certain limits, an analysis that shows you the impact of inhomogeneity in detection. What do I mean by inhomogeneity? Well, I can parameterize the coupling strength of the atom to the collective readout with a factor eta, which varies between 0 and 1, which describes where the atom sits in the mode function of the lattice. Because we had this nearly perfect registration to start, all the etas, let's assume, are close to 1 for the state prep. Now the atoms are released from the lattice, they explode, they're refocused, and we have now a distribution of etas. The atoms are at different positions, and in particular, if we know the position of each and every atom in that final distribution, then we can construct this quantity, which is the effective number of atoms that have been detected related to these inhomogeneous couplings. And from that effective atom number, we can infer this quantity P effective, which is basically something that describes the loss of homogeneity, parameterizes that, N naught is the initial number of atoms. And from these two parameters, you can make precise predictions about the variance, the phase variance that you expect to be able to observe after the sequence compared to the initial squeeze state variance. And it's a remarkable, given the complexity of what's going on, this is a remarkably simple parameterization. And this is a theory that you can test. And so that's what this data shows. I won't go into the details of the experiment, but for the first time, I think we've quantitatively validated, what are some of the engineering paradigms that need to be used to obtain excellent squeezing performance. This is effective loss, which changes when you change the release time. Longer release times where the atoms are in free space for longer lead to greater inhomogeneity, and this is the observed variance. And so this is where you have basically short release times. This is where you have the longest release times, and you see a degradation in the observed phase variance. And you can look at that data a different way. This is the release time in milliseconds, and this is the observed phase variance. This is the value that you associate with shot noise for N0 atoms all homogeneously coupling. And this is the initial squeeze state, and then this is the reduction in phase variance that's observed in back-to-back measurements as a result of the increasing inhomogeneity associated with the release and recapture protocol. Now, as you get to these longer times, actually the effective number of atoms decreases. So in terms of entanglement metrics and things like that, what you want to compare to is what's the shot noise on the effective number of atoms, and so those are these points here. So even out at 3 milliseconds, you still have entanglement in this distribution. And this just goes to show you that, for this protocol, after about a millisecond, you're starting to get in trouble. You're starting to get to a point where you're degrading the impact of your state squeezing. So, but a millisecond is actually not, that's actually starting to be a useful time for a real clock. I'll show you this in just a minute or two. I've probably got 3 more minutes, and so I'm not going to blow through to a 50-minute talk here. But let me talk about strategy 2, and then I'll wrap it up. So strategy 2 was, rather than release, refocus, and detect in the lattice, let's not try and go back into lattice at all, because after all, that's causing us pain because of that mode coupling function of the lattice. Let's go into free space and observe the atoms in fluorescence. Well, that's easier said than done, because there are lots of ways that you can have inhomogeneous mode readout with fluorescence. Like, your fluorescence probe has to be perfectly uniform over the distribution. Any speckle in that laser beam is trouble, and so on. So it's important to implement this properly. We're starting to get there, but I don't think we're fully there yet. So here's the complicated timing diagram for this. So make the squeeze state in the lattice, release into, turn off the lattice. Lattice is gone now. Clock interrogation, and then a fluorescence imaging protocol. And this is the data that shows the picture of the spatial distribution associated with the 2 atomic states. They're separated with a short pushing pulse. And we collect the scattered light and focus it on a low noise CCD camera. Data on the right here is meant to show how effective this can be in preserving just the noise correlations from the state prep to the detection. And so on one axis you have the inferred noise associated with the QND probe. That's on the first one. That's on the vertical axis, and then on the horizontal axis, you count the atoms that after you've made the squeeze state, and you hope to get the same number. And so a parametric plot of the atom or the transition probability in fluorescence should reveal, kind of ideally just a line, but of course you have noise, and that blends that line into something more elliptical. And what you're looking for is a distribution that collapses like this if you have, going to have excellent fidelity between your preparation and your detection. What this is showing is we have some fidelity, we have some squeezing resulting from this protocol. So, we spent months years trying to improve that. But this is where we are right now. With this fluorescence readout, we are basically 6.4 dB below the classical projection noise limit. And this is kind of a parametric study of clock Allen deviation as a function of the interrogation time of the clock. And you can see that this clock runs at a very low rep rate, one shot per second. So we're not going to expect a beautiful clock, but it's starting to get pretty good. I mean, we're starting to get at these longer interrogation times clock Allen deviations, which are competitive with state-of-the-art stuff, and it averages down appropriately so that you can get some pretty good noise performance out of an interrogation sequence. We don't expect excellent long-term performance because nothing about this apparatus has been engineered to be a proper clock. But at shorter time scales, we sort of do. And if you look at the numbers we're putting up there, what I want to say is they're starting to get close to state-of-the-art practical standards. So this is state-of-the-art practical standard. This is the Microsemi 5071A, formerly Hewlett-Packard, of course. And you see that noise at a second for standard performance is about 10 to the minus 11 Allen deviation. That's where we are with this state squeezing right now. And the higher performance units obviously have slightly lower noise. The reason I'm putting this up there is just to orient you to where we are now and where I think we can go. And say like world wants to have something better than that, we do. then state squeezing ultimately is going to take us there. And we are now right at the cusp. I don't want to call it quantum supremacy for clocks because there are other ways of getting better performance. But I think in the next few years, we are actually going to start to see time standards, technologically useful ones, that just like the LIGO detectors are just, you're going to want to use squeezing to make them better. So I had wanted to say, I'm out of time now. I want to say that, so what are we doing in my lab right now? Well, we're kind of, I feel like we can't go any further with the clocks. Now you need an engineering team to come in and do that right. So we're paying attention to atom interferometry now and seeing if we can bring these same protocols into atom interferometric sensors. And the sort of amazing thing this is a plot that shows de Broglie wave functions splitting up and then recombining. The sort of thing that's amazing is if you do state squeezing with interferometry, the states that exist at the regions where the wave functions now for the macroscopic ensembles are separated, they're entangled, but over large distance scales. And in my group, we've made that distance scale as much as 50 centimeters. And so what we're trying to do now is show the same sort of quantum enhancement for measurements that benefit kind of tests of relativity, gravitational wave detectors, and so forth, but where those ensembles are now, from the point of view of fundamental foundations of quantum mechanics, it's just remarkable. You asked the question, how does nature let this sort of thing work? It's like how I'm having ensembles of atoms entangled over half a meter, and somehow also doing good precision measurement. I'd like to see if quantum mechanics lets me do this. So I want to conclude just by saying that not every sensor is going to benefit from this. The ones that all you're looking for is accuracy at the output, and you don't need stability, don't bother using state squeezing. It's not going to improve your accuracy. It's just going to help you integrate down to your quote flicker floor or the observable faster. If you're noise starved, states like LIGO was, state squeezing is an appropriate thing to do. If you're not noise starved, don't go through the hassle. So what are some examples of noise-starved measurements that we're doing? Well, one is orbiting gravity gradiometers are noise-starved based on atoms. And so state squeezing will have a big impact here. I'll skip this slide and say another measurement, and this is a slide from my colleague Jason Hogan, who is PI on this program called MAGIS 100, where we're using atom interferometry to build a dark matter and gravitational wave detector at FNAL. Bottom line is to build, if you could talk about this detector as a gravitational wave detector, it could have great noise performance in certain parts of the gravitational wave frequency band. In order to realize exceptional noise performance in this sensor, you've got to use state squeezing. This is where we think we can go. Other factors obviously are going to get in the way, maybe, but never going to get there without, like LIGO, doing quantum metrology. So that's all I have to say. Here are the people I have to thank, and of course, thank you for your attention early in the morning.
Questions? I traditionally would have thought for a nice local oscillator clock that that's before your talk just now, I would have always thought that state squeezing wasn't the way to go because you could always just increase the atom number, and that it was going to be in high accuracy clocks where you wanted as few atoms as possible that state squeezing was going to be a big value. And you're arguing here very convincingly, I think, the reverse of that. And I'm still trying to get into my head, can I, in a very applied sense, primarily think of this as a way to make the clock smaller? That I could, if I have a state squeezing of 100, if I have a squeezing of 100, I could just have 100 clocks?
Yeah. Sure. Yeah. I mean, it's a way of, at the end, the utility boils down to a bunch of engineering trades. And I should have said it, but most atomic sensors right now are operating, the well-engineered ones are operating at the maximum flux that we know how to get right now. It's not to say that a person couldn't invent a higher flux atomic source, but those atoms are nasty. They bang into each other. They're systematic shifts. So like in our precision gravitational sensors, you don't want to have more than 10 to 6 atoms in an ensemble. You start to see mean field interactions between the atoms. Fountain clocks are running at the 10 to 7 atoms per shot is about the max they can have. Vapor cell clocks, which I think is a very promising candidate for state squeezing, you can't have more than 10 to 12 atoms you won't get accuracy out of that. So all practical clocks are limited by atom number. The only way of driving that noise down, do this. I could have 100 clocks and I'd do just as well.
So how you're combining your squeezing with atom interferometry? Are you just doing runs every day after preparing the squeeze?
Yeah, so there's actually a little subtlety in that, what the pulse sequence has to be, and it's still the subject of exploration. It's not just Ramsey-Bourdais. So it's something, the protocol is microwave pi over 2, 4 optical pies, and microwave pi over 2 is the one we think is going to work the best. But that's... I shouldn't have even said anything. So that's ultra preliminary. Like it hasn't worked yet. So.
Questions? So, going way back to the notion of doing a kind of bell test with your spin squeezed ensemble, which I understand you want to sort of spatially separate things and then do some sort of spatial resolution and atom statistics. How does that work?
Oh, I had the Bell witness there, and so in order to turn a Bell witness into the Bell test, you actually need to be able to get into the ensemble and for each spin in the ensemble do such a correlation, something technologically impossible. So then I think the question you asked is it possible to do how would you do a Bell test today? And I think the way of doing that is to spatially separate an ensemble, bifurcate it, and then do correlations between two aggregate ensembles. And so what we have in mind, and this is sort of half-baked, it's aligning with what we're doing in the interferometry where we're spatially separating the ensembles, is pi over 2 pulse, state squeeze, and then momentum recoil, state-dependent momentum recoil to separate out 2 ensembles, and then correlated measurements to do Bell tests where the correlation is as a function of a microwave rotation on one of the ensembles versus the other. It might work, it might not. But in the end, I think stuff like Monica Schleyer-Smith is doing, where she has access to individual atoms in the ensemble, might allow other types of correlation measurements that are Bell-like. So, emerging direction.
Well, could you say a few more words on the matches, the current status, and the relation to the dark matter searches?
Yeah, so MAGIS is there for the ultra light dark matter, and if you're interested in heavier stuff, I think the superconducting sensors are the way to go. But there's room for clocks at the left hand side of those QCD Axion type dark matter detection charts. I didn't put it in here, so that's where I think MAGIS and other atomic clock detection methods are going to have their impact. In terms of the status, it's now well enough funded that we can actually build what we think we want to build, and we're starting to get engineering drawings out of Fermilab, and like safety engineers worrying about how to install the vacuum pipe. So I think we're going to look for first light out of the atoms in 3 years. There's a lot of parts that have to come together, but it's now feels just like there's an engineering roadmap with a bunch of Gantt charts and things like that, and then the rubber will hit the road when we start, looking at the noise performance of the sensor in 3 years.
How deep is it going to be?
It's a 100-meter. It's in the NUMMI shaft at Fermilab, so it's a 100-meter shaft, and that works out. We'd like to go to a place where we have access to larger baselines. Kilometer scale would be something I think might be optimum. Yeah. China might get there first.
Question?
Thanks a lot.